Back when you were watching the waves videos, you saw what happened when you let plane waves run through two slits. You'd get this interference pattern where there would be some crests and crests interacting and some troughs and troughs interacting, and you'd have different interference. And we'd actually end up with like these streaks of nothingness, maybe where there was all destructive interference and then really bright places, lots of interference there too. And you can do it with sound. If you see a little guy near a speaker, we've got sound waves coming out. At some places the sound waves will interfere constructively and you'll get like darker and brighter areas. In some places, if you see this line here where it looks like it's just gray, you'll get destructive interference. So we'll get loud areas and not very loud areas. Well, it turns out the same thing happens with light. If you shine light through two slits, what comes out is this interference pattern that's shown over here on the right, where you have some bright places and you have some dark places. Bright places, dark places, bright places, dark places. Now, that should actually surprise you. You might expect that if you shone light through these two slits, that what you would see would be two strips of light with a dark part in the middle. Why is it that light would spread out in this way where you have a whole bunch of fringes? So it should be surprising that that happens. It happens because light is a wave, and just like the water waves bend when they pass through these holes and then interfere with each other, light bends when it passes through those holes and interferes with each other. And you get this crazy diffraction pattern just from these two slits. I'll show you this tomorrow. The slits actually have to be very small, and so I have special slides that I can use to show you this. What's happening is, when light goes through there, so imagine we send out light from a laser, and here are the waves that hit the slits, you get some crests and troughs, and they interfere at certain places, some places to make it really bright, some places to make it really dark. So if we put a little strip of film there, we would actually capture really bright and really dark places. And I got a little graph here that shows kind of the intensity of the light. So some places really bright, the peaks, lots of constructive interference, lots of destructive interference at the valleys where it's really dark. Again, it should be shocking that light shown through two holes will make this pattern with a bunch of holes. Like, you would not expect that from just light going through two holes. Now again, the reason that's happening is you've got constructive and destructive interference. At places where you get two crests matching up from the waves that went through those two holes, that diffracted through those two holes, you'll get a bright area from constructive interference. At places where you've got destructive interference from the light waves, you'll get a dark area. And so if we kind of expand that image I just showed you, we'll have waves go through the holes, interfere with each other in kind of this big mess, some constructive interference, some destructive interference, some constructive, some destructive, some constructive, and we'll get bright and dark patterns. We can predict, though, where it will be bright and where it will be dark using this equation. Now this seems to be going very fast, I imagine. That's because I want to get the hardcore math in tonight, show you that, and then tomorrow I can deal with the concepts and show you some demos and examples. So with double slit interference, when you have light passing through two holes, you can predict where the dark and bright areas are going to be. This is the equation that does it. D sine theta, and D sine theta, by the way, is the path difference. So that's if we measure from the hole how much difference is there from this one wave that went through one hole and this other wave when they meet. So we need to know if their crests are going to meet or if their troughs are going to meet. And so we use what's called the path difference. What's the difference in their length because of that angle? So they each travel a little bit different distance because there's an angle between their starting points. D is the distance between the slits. Theta is the angle, and that's what I was just talking about in this little drawing or picture I made here, that there's an angle we can measure between the two starting places. And then M is if you're counting from the center of the interference pattern, so like if we had two slits and shone a light through the two slits, so maybe light passes through two holes, and we get bright and dark patterns. We're going to count from the one that's parallel, so the one straight across. So tell me which bright fringe you want to know, and we number those 0, 1, 2, and 3. Tell me which dark fringe you want to know. We number those 0.5, so imagine if this is 0, the one that's right in the middle, the next bright place is 1, so the dark place in the middle is 0.5. So that's m, telling me which one you want to look at. And then lambda is the wavelength of the light. And this equation basically tells us where each bright and dark spot will show up. It all seemed complicated, but I think if we try this, you'll get to see that it's fairly simple. So two slits that are 4.8 by times 10 to the negative 6 meters apart are illuminated by parallel rays, so light comes in. They form a fifth order bright band, so that means m equals 5. So when you see fifth order bright band, that means the bright band is 5 from the center. So this phrase right here means m equals 5 in that equation. At an angle of 30 degrees from the center line, what is the wavelength of the light used? So the d in that equation, this is a good clarification point, maybe something I should have said in the last slide. So if we're thinking about d sine theta equals m lambda, d is the distance between the two slits. So that's this distance here, distance between the two slits. Not, and that can be confusing, not the distance to the wall where the light is being shown. The angle handles that. So now if I just do d sine theta equals m lambda, it's asking me for wavelength lambda. So if I divide by m on both sides of this equation, and then bring it down here, get d sine theta over m equals lambda. And this is a pretty simple plug-it-in equation, 4.8 times 10 to the negative 6 meters times the sine of 30 degrees divided by 5. And that should give you 0.48 times 10 to the negative 6. Or if you move the decimal a bit, you'll find that it's 480 nanometers. Just a good time to point out that even though meters remains the standard unit for measurement of distance, nanometers is typically used when talking about light, and so you just seem a lot more professional and like you know what you're doing if when talking about light you go ahead and convert it to nanometers. So go ahead and make it something times 10 to the negative 9th, and then write that as nanometers. That's just kind of the standard way of dealing with light. Nobody's going to count it wrong in the AP exam or anything like that, but just someone will notice that you've done that if they understand physics, and they'll think that you know what's up. Alright, light of wavelength 4 times 10 to the negative 7th meters falls in a pair of slits, and the third order bright band falls in an angle of 30 degrees from the main beam. How far apart are the slits? So now we're looking for D. Now this can be deceptive. You gotta watch out here. This is the wavelength of the light. And if you were just like trying to do matching variables to their units, you might think that that should be D. But D, when you got D sine theta equals m lambda, the only units in that entire equation are meters, or nanometers if you're being professional about it, because the D would have units meters because it's a length, and lambda would have units meters because it's a length. So you got to be careful there. You can't depend on your units on this one to know what goes where. You've got to actually watch. Sine theta has no units, and m has no units. It's just a number. So let's do this. We want D, so if I solve that equation by dividing by sine theta, I get D equals m lambda divided by sine theta. And if I plug in what I've got, I'm looking at the third order bright band, that's m equals 3, 3 lambda, the wavelength of the light, 4 times 10 to the negative 7th meters, divided by the sine of 30 degrees. If you carry out that math, you get 2.4 times 10 to the negative 6 meters. And if you wanted to, you can convert that to nanometers. It's a little less necessary because they were asking for distance and not lambda. Lambdas are usually conveyed in nanometers, so it's actually a little surprising that this was not written in nanometers. I might want to take a second and convert that just for practice. You should get something like 400 nanometers. But anyway, there's our distance, and that's how you tell where the bright bands will be and how far apart the slits are, that kind of good stuff. We'll look at lots of demos with this tomorrow, so hopefully the concepts will make more sense, but I do want the math to be in your head when you walk in tomorrow.